the first thing that we want to talk a little about is the normalization and some boundary conditions, because otherwise we can't really understand what's going on. And happily, the discussion is not that complicated. So we want to normalize. So what do we want? Integral d cubed x psi ELM of x squared equals 1. So clearly, we want to go into angular variables. So again, this is r squared dr integral the solid angle, r squared er, and this thing is now u el over r, I'm sorry, u el squared, absolute value over r squared. Look at the rightmost blackboard, u el of r. I must square it, because the wave function is squared, over r squared. And then I have ylm star of theta phi, ylm of theta phi. And if this is supposed to be normalized, this is supposed to be the number 1. Well, happily, this part, this is why we needed to talk a little about spherical harmonics. This integral is 1 because it corresponds precisely to L equal L prime, M equal M prime. And look how lucky or nice this is. R squared cancels with R squared, so the final condition is the integral from 0 to infinity dr uel of r squared is equal to 1. Which shows that kind of the u really plays the role of a wave function on a line. And even though it was a little complicated, there was the r here and angular dependence and everything, a good wave function is one that is just think of psi as being u, a one-dimensional wave function, psi being u, and if you can integrate it squared, you've got it. Because I had to square this, so there was u over r. Oh, I'm sorry. That parenthesis is a remnant. I tried to erase it a little. It's not squared anymore. The square is on the absolute values r squared. So this is good news for our interpretation. So now, before I discuss the peculiarities of the boundary conditions, I want to introduce really the main point that we're going to illustrate in this lecture. This is the thing that should remain in your heads. It's a picture, but it's an important one. You basically, when you want to organize the spectrum, you'll draw the following diagram. Energies here, and L here. And it's a funny kind of diagram. It's not like a curve or a plot. It's like a histogram or a kind of thing like that. So what will happen is that you have a one-dimensional problem. If these potentials are normal, there will be bound states. And let's consider the case of bound states for these purposes of this graph, just bound states. Now you look at this and you say, OK, what am I supposed to do? I'm going to have states for all values of L and M and probably some energies. So M doesn't affect the radial equation. That's very important. But L does. So I have a different problem to solve for different L. So I will make my histogram here and put here L equals 0 at this region. L equals 1, L equals 2, L equals 3, and go on. Now, suppose I fix an L. L is fixed. Now it's a Schrödinger equation for a one-dimensional problem. You would expect that if the potential is suitably grows, which is a typical case, E will be quantized. And there will not be degeneracies, because the bound state spectrum in one dimension is non-degenerate. So I should expect that for each L, there are going to be energy values that are going to appear. So for L equals 0, I expect that there will be some energy here for which I got a state. And that line means I got a state. And there's some energy here that could be called E 1, 0. Is the first energy that is allowed with L equals 0. Then there will be another one here, maybe, E, I'll write it down, 2, 0. So basically, I'm labeling the energies with E, N, L, which means the first solution with L equals 0, the second solution with L equals 0, the third solution, E, 3, 0. Then you come to L equals 1. And you must solve the equation again. And then for L equal 1, there will be the lowest energy, the ground state energy of the L equal 1 potential, and then higher and higher. Since the L equal 1 potential is higher than the L equal 0 potential, it's higher up, the energies should be higher up, at least the first one should be. And therefore, the first one could be a little higher than this, or maybe by some accident it just fits here. Or maybe it should fit here. Well, we don't know, but there's no obvious reason why it should, so I'll put it here. L equal 1, and this would be E 1, 1. The first state with L equals 1. Then here could be E 2, 1, the second state with L equal 1 and higher up. And then for L equal, my diagram is a little too big. E1, 1, E2, 1. Then you have states here. So maybe this one, L equals 2, I don't know where it goes. It just has to be higher than this one. So I'll put it here. And this would be E1, 2. Maybe there's an E2, 2. And here an E1, 3. But this is the answer to your problem. That's the energy levels of a central potential. So it's a good, nice little diagram in which you put the states, you put a little line wherever you find the state, and for L equals 0, you have those states. Now, because there's no degeneracies in the bound states of a one-dimensional potential, I don't have like two lines here that coincide. Because there's no two states with the same energy here. It's just one state. And there's one here. I cannot have two things there. That's pretty important too. So you have a list of states here, and there's just one state here, one state. But as you can see, you probably are catching me in a little wrong play of words, because I say there's one state here. Yes, it's one state because it's L equals 0, one state, one state. But this state, which is this should be called one single L equal 1 multiplet. So this is not really one state at the end of the day. It's one state of the one-dimensional radial equation, but you know that L equals 1 comes accompanied with 3 values of m. So there's 3 states that are degenerate because they have the same energy. The energy doesn't depend on m. So this thing is a 1 L equal 1 multiplet, which means really 3 states. And this is 3 states. And this is 3 states. And this is 1 L equal 2 multiplet, which has possibility of m equals 2, 1, 0, minus 1, and minus 2. So this state is just 1 L equal 2 multiplet, but it really means 5 states of the central potential. 5 degenerate states, because the m doesn't change the energy. And this is 5 states. And this is 7 states, 1 L equal 3 multiplet, which contains 7 states. Okay, so questions. This is the most important graph.